Oh, the streets.
Alrighty, here we go. So,
Tell
tell me what you know about this. We're going to give it about, I don't know, 10 minutes max. So I'll set a timer, and then we'll move on.
Lucas dead again.
What?
Lucas dead again.
Oh, yikes. So, what can you add to this diagram? Zayden, what do you see?
I say that all,
Guys, you can if you want.
all those right angles, I just made them right angles.
Okay, cool. So these all have to be right angles, right? Because these are boxes, which means this is a right angle. And then by LPT, these must be right angles as well. So that's cool.
No, it's actually Tuesday. Got me.
So these are all right angle triangles. Cool.
What's the week?
218. Week of the 18th. Anybody else see anything?
If you do vertical angle,
Where?
like 12 and then the square.
Like here and here?
No. Like the bottom 12.
The bottom 12.
Yeah, and then the big triangle or the big.
Here and here?
Yeah.
Nah, I can't do vertical. That's 180 definitely. That's 90. What else do you see?
Those angles in the right triangles on the right side, those three, their top angle, I think, should be the same because they're all hitting at the same angles.
Nice job. Second person to get this today. So here's how we know that these triangles have the same angles. So if I extend these lines out, notice that we have two parallel lines and a transversal. Actually, we have three, bottom here and here, and a transversal. How do I know they're parallel? Because they're all running at 90. We have corresponding angles here. So these angles are all going to correspond, which means these are all running in the same direction, which means they're parallel, which means these angles are going to be the same as well. So now what do we know? Angle, all these triangles are similar, right? So this triangle is similar to this triangle, is similar to that triangle. And now why are we interested in those triangles, right? We're interested in getting the area of the square. Why do we care about those triangles? Anybody?
That's
The hypotenuse of those added up will get
We'll get the side of the square, and if we have the side of the square, we get the area, right? If the side is 5, then the area is 25, right? Good idea. Well, we get these angles for free too, just so you know. Right? Whatever's left over must be the same. So again, these triangles are all similar. What else do we know?
if you, I don't know how this would help, but if you add up 12, 12, and 3, you get 27. So that's like equivalent to the big one.
These three boxes would add up to 27. We get 24 plus 3 is 27, so that's interesting. I'll write that down. So there should be some way, in theory, and you have to be probably allowed to cut up these boxes, right? But you could fit them all inside here. That's kind of interesting.
Couldn't you say that there's a right angle inside the square?
Yep, these would be right angles as well, because it's a square. Right? And these sides would be congruent. Now this is a tough problem. if you can't solve this problem, then find an easier one. One way to make this easier might be to say that we know the sides of these. Maybe that's 3 and 9, right? Again, it's okay to change the problem. It doesn't answer this question, but it does solve a similar problem. And when you do this stuff with a warm-up, right, you say, I'm going to make that a 9 and a 3, I'm going to solve, right? That's not related to that's not the same problem as a warm-up, but it is related. I'll give you self-development for that. So if you want to go home and tackle that and say, if I know that this is 9 and this is 3, I can solve it, right? Or maybe you know all these are squares and not just boxes, right? If this was a square right here, what would the sides of the square be? Better question. If this was a 4, what would the sides of the square be? 2, right? When we say something is squared, it means putting it on a square. So like when I say 2 squared, I mean 2 squared. 2 put on a square. What's the area of this square? 4, otherwise known as 2 squared, right?
Yeah.
So if I have 3 on the inside, what I'm asking is, what number times itself gets me 3? Well, how did you find, well, if this is 4, this gets us 2, right? It's the square root.
6.
So these sides are the square root,
It'd be 9.
right? Same thing. So this simplified to 2. What side would this be? Be root 3, which does not simplify to 9. You see what I'm saying? The area is 4, so when I root that, I get the side. The area is 3, so when I root that, I get the side. This one simplifies, right?
No.
This one does not. What is root 3 approximately?
Probably like 1.
It's got to be between 1 and 2, right? Because root 4 is bigger than root 3, right? And what is root 4? 2, right? And root 1 is 1, so it's got to be between 1 and 2, right? Because root 1 is less than root 3, which is greater than, or less than root 4, right? Root 3 is somewhere between these, and we know that that's 1 and that's 2. So root 3 must be between 1 and 2, right? That's the estimation. Does everybody see that idea? Right? I know root 1 is 1. I know the root of 4 is 2. Root 3 is between 1 and 4, so it must be between their roots, 1 and 2. So it's 1 point something. Pretty close to 2, right? What about root 27? Because that would be the side of this if it was a square, right? Root 27. What's root 27 approximately?
Between 5 and 6.
Between 5 and 6, right? Somewhere between these two. Because 5 squared is 25, right? Root 27 should be bigger. 6 squared is 36, so it's going to be really close to 5, right? Really close to 5. Okay, fun fact. So would it be easier if we assume these are squares, right? You can investigate that. We'll work on this problem the rest of the week, as is. But if you want to investigate it, assuming that these are squares, or that this is 9 and that's 3, and then go from there, that's cool. Anything else we can add to the diagram? Anything else we can figure out? Yes, no, maybe?
You could do the other triangle in between 12 and then
This one right here?
yeah.
What do we know about this triangle?
We have one angle.
Yep.
Then could you do by like LPT with the middle?
Yeah, so check this out, guys. Doesn't this all add up to 180?
Yeah.
Right? We've got orange and red. So orange and a right angle. Well, don't all these add up to 180? Orange and red. What's left over? Blue. So what must be left over here? Also blue, right? I'm going to say that again. This is all 180. 180 minus orange minus right angle gets us the blue angle, right? This is 180. 180 minus the orange minus the right angle must also get us the blue angle. So yeah, by LPT, this must be blue as well. And so what do we know about this triangle?
Any line is similar.
Yep, it's similar to all the others. So again, we get orange here. That's kind of cool. And then, of course, since this is 90, what does that mean about the angle right here?
Blue.
It's blue.
Whoa.
That's kind of cool. So all these are similar. Not bad.
So I'm trying to find the area.
The area of this square. Up, time's up. Sorry guys, that's it for today.
You gave me PTSD.
Did I?
I wake up.
Wow. I'm glad that I have an impact on kids. All right, let's put this away. Not bad, guys. Good job with the similar triangles.
Now we do good math.
Mr. Matt, do we need to keep any of the stuff from first semester?
Not necessarily, but if you want to use it in your portfolio, that would be a good idea. Right?
I'm gonna just take it and like put it in my locker.
That's cool. I've got people that store their portfolios in that closet right there. Not that one, but the one over.
My
I don't have infinite room, but I do have room.
so full it needs to be.
Yes, you should. You should definitely have a stuff that I need right now binder and a stuff that I'm putting away in an archive, right? Alrighty, so let's talk about special segments and triangles.
Yay.
Special segments. Now, we already know about some triangle segments, right? We learned about mid-segments last week when we did that one proof. Remember, a mid-segment is when we connect the medians together. Oh, you didn't get one? I'm guessing you didn't get this either. So remember, mid-segments connect a midpoint to a midpoint. So not this. But when we have a triangle, right? Triangles always have midpoints on their sides, right? There's always going to be a middle. And if we connect those guys up, we get the triforce, which of course, these guys are mid-segments. And we call them mid-segments because they are connecting the midpoints. And we know that this segment right here, because of similar triangles, this guy right here will be half the amount that this is, right? So if this is 2, that would be 1. And not only that, but they're parallel, right? We proved that last week. Same idea if we turn it. If this was 4, then that would make this guy 2 in here, right? They're always related by half, and they're parallel. So that's special properties of mid-segments. There are some other segments in triangles we're going to talk about. We're going to prove them. Today we're not doing any proof. My hope is that tomorrow we will be, since we do not have an early dismissal. Thank God. I was really worried we did. All right, so let's talk about this. I got a lot of stuff to get done, guys. We've got a ton left to do for quarter 3 and quarter 4, and I want to give you as much time in quarter 3 to get trigonometry as possible, because we're going to have an intro to trig, and that's going to cap off 3 and probably spill a little into 4. So I want to make sure you have as much time as possible. The more time we have, the better. All right, so medians. Not to be confused with mid-segments. Remember, mid-segment connects what to what? What does a mid-segment connect? Midpoint to midpoint, right? A median is vertex to midpoint. Now, a vertex, like a vertex of the angle, is where the angle comes together, right? It's the middle part of the angle. Now, why do we call a triangle a triangle? 3 angles, right? So, vertex of one of its angles, vertex of one of its angles, vertex of one of its angles. The vertices of the triangle are the pointy parts, right? The vertices of, and vertices is plural for vertex, right? They're the vertices of the angles of the triangle. So if I go from vertex to the midpoint, I get a median. Now, a lot of people say vertex to the midpoint of the opposite side, but yeah, that's the opposite side's midpoint. But how could I connect this vertex to this midpoint, right? I couldn't. I'd have to go from here to here, and what would I get? Right? I just get halfway point on that side. Not very interesting. So we're going from vertex to midpoint. I could also go from here, vertex to this guy's midpoint, right? And vertex to this midpoint. Those are all medians. So let's talk about what medians do and their special little properties. Actually, we'll do that in a second. Let's go down to angle bisector. We'll confuse you as much as possible to start out. So angle bisector. It's called an angle bisector, this line right here, because it bisects an angle of a triangle. It cuts it into 2 equal pieces. Does everybody understand what that symbol means? Right? Cool. So yeah, I could draw one here, and it would cut this guy in half, right? And this guy would cut it in half, right? Where it intersects on the opposite side does not matter. That's not necessarily halfway, right? Doesn't hit any special angles. All we're saying is if we cut the angle in half, that's an angle bisector. We cool with that? So median, vertex to midpoint, angle bisector, bisects the angle.
Would those be congruent?
Say it again?
Would those be congruent?
what would be congruent? These two angles would be congruent here, because it's angle bisector. This one, congruent there and there? Not necessarily. Could a median also be an angle bisector? Sure. But that's when this happens to bisect the angle and hit it halfway, right? Could be both. Coincidence. All right, next one. You've been calling it height your whole life. The height of the triangle, right, from here to here. Now, if this is the base, then that's the height. If I rotate it, now this is the base, right? And the height's like here, right? So it depends on which one we're calling the base. There's a bunch of different heights we can draw. But really how you do it is you just go from a vertex straight down to the opposite side to hit it at 90. From here, straight across to hit it at 90 would probably be like there, maybe. And then from here across to 90 would be like there. So you go from the vertex to the opposite side at 90 degrees. We can call these perpendiculars because they are perpendicular, right? They hit at 90. We can call them heights because the height of the triangle is always right. And then altitude, like height of a mountain. The one that you're going to want to be most familiar with is orthogonal, which kind of sucks because it's the biggest one, right? So here's why orthogonal and perpendicular are different things, even though they mean the same thing. So in 2 dimensions, the red pen and the black pen are perpendicular, right? See, they hit at 90. Right? Any 90 degree is going to be perpendicular. But what if we had 3 dimensions? This is orthogonal. 90 degrees in all directions. So the orange is perpendicular to the red, and it's perpendicular to the black. And the black is perpendicular to the orange. It's like super perpendicular. Now check it out. If I were to go like this, yes, black and red are still perpendicular. But are they perpendicular to this? No, there's not a 90 degree there.
So they're not worth.
They wouldn't be orthogonal. We have black and orange perpendicular, right? But not black and red. Does that make sense? Black and red, not 90 degrees?
So
You
like
cool with
a
that?
cube?
This is 90 degrees between black and orange. Question, is black and red, are they 90 degrees?
Wait, what?
They are, aren't
Black
they?
and red?
Black and red are 90 degrees to each other. 90 degree angle here.
Black and
What?
red?
Wait, explain again, please.
Black and red or orange and red?
Do you see it? Oh, I'm sorry. Orange and red, orange and red, orange and red, orange and red, orange and red.
Okay.
Okay, good. Sorry. Colors are hard, guys. Colors are hard. I've been calling orange green for the last 2 days. This is not good.
I was like, how is
My sister always had trouble with her colors and with her right and left, so when we played Twister, we'd always mess with her. Be like, right hand on red, and she'd be like, right, and she'd be like, green, left hand, no. And then when she would get it right, we'd still pretend she got it wrong, which is probably why she still sucks at her colors and handedness today. No, Kayla, your other left, and it would literally be her right, her correct hand. I thought it was funny. That's what big brothers are for. All right, so for something to be orthogonal in 3 dimensions, it's pretty specific, right? That's orthogonal. So we have a different word for perpendicular and orthogonal, right? Now, in 2 dimensions, well, it's orthogonal is the same thing as perpendicular, right? There's only one way to do it, right? So they're interchangeable in 2 dimensions. You're going to want to remember orthogonal because it's going to be a word that we're going to use a lot to describe something in a second. So, recap. Vertex to midpoint is a median. Angle bisector is where we bisect the angle. And the orthogonals are the heights or the altitudes or the perpendiculars of the triangle. We cool that? From the vertex to the opposite side at 90. Does it hit it in the middle? Not necessarily, right? Perpendicular bisector. This is a weird one. This is a weird one. It's perpendicular because it's 90 degrees. It's bisecting not an angle, but a segment. So it goes from the midpoint straight up. A lot of you guys are going to try to draw these and you'll be like, I want to go from here to there because I want perpendicular bisector, but how do I make that a right angle? And you can't.
No.
It's not possible.
Right part is supposed to do the same.
What you do is you find the midpoint and go straight up from there. Okay. Median, vertex to midpoint. Angle bisector, bisects an angle. Orthogonals, they're the heights of the triangles, right? Just 90, that's all we care about, vertex to 90. And then perpendicular is midpoint to 90. Midpoint going up at 90. Cool. Think you got them? Vertex to midpoint, median. Angle bisector, everybody loves that one. Does it hit in the middle? Does it hit any special spot? No. It just cuts the angle in half. That's all we're saying. Angle bisector. Height. Drops from a vertex down to 90. Does it cut it in half? No, not necessarily. Right? Nothing special. Just hits it at 90. And then perpendicular bisector is a weird one. It's very specific. Okay? Midpoint and up at 90. Feeling good?
Yes.
All right. Let's take a look at the next piece of paper. Bum, bum, bum! Yes. Of course. Tell which center each diagram is portraying, where the center is located when the triangle is acute, right, or obtuse, what segments are used to create the center, and any special properties that those centers and segments have. All right, so you don't know about the centers yet. But we know about the segments. Let's go through. What kind of segments do you see in triangle number 1? I gave you a list of 4. Median, angle bisector, perpendicular, altitude, height, or orthogonal, and perpendicular bisector. What do you see? Angle bisectors, right? All the angles are cut in half. Yes. You didn't get one of these? Wow. How unprofessional. Those are angle bisectors because they cut the angles in half. One half. Number 2.
That does not sound good.
What do you see here?
A right angle.
Yes, you do. So they're perpendiculars. Are they orthogonals or perpendicular bisectors? Orthogonals, right? Perpendicular bisectors hit at 90 and cut the side in half, right? Do these cut in half?
What?
No. These are heights of the triangle. Focus on one at a time. CCE. It's the height of the triangle. If AB is the base. If CA is the base, then BD is the height of the triangle.
Are these supposed to be 3D?
They're all 90, yes.
No, like 3D?
No, they're not. But are you seeing it in 3D?
I don't know.
Trippy,
what I'm
man.
saying.
Sometimes that happens to me. All right, and then BC is the base, then that means AF would be the height, right? So there's 3 different heights. Well, are all the heights the same length? AF would be the height if BC is the base, right? So there's 3 different heights that you can find. Now, no matter how I turn the triangle, the area is the same, right? If I turn the triangle, does the area change? No, it's the same triangle. But depending on which height I choose, aren't some heights longer than others? Isn't area of a triangle half base times height? So if the height can change, how does the area stay the same? That's trippy. Well, it turns out the way the height changes, right? See, when the height is small, the base is big. And when the height is big, the base is small. They balance each other out, right? Isn't that crazy? So it'll always be the same area, right? Because when you turn the triangle, the area is always the same, right? But depending on which combination of base and height you choose, you'll get different numbers that'll multiply together to make the same area. Cool. So maybe this base is 5 and this height is 4. That makes 20, right? Well, this height is bigger, so maybe its height is 5 and this base is 4. Right? And this one looks like it's somewhere in between. So maybe it's, I don't know, 10 and 2, or I don't know, I made it up. Didn't sound like it was in between. I ran out of nice numbers. So cool. These are orthogonals. We're going to call them that. Orthogonal means height, means altitude, right? It's the height of the triangle, but it's perpendicular. But we're going to use orthogonal because it's going to help you with what we're going to learn later. Orthogonals. Are you having fun?
No.
This is what geometry could be normally if we just did definitions and you had to write that stuff down. This week is going to feel like that. And you're actually going to prove this stuff later. We're going to do that next week. I'm just giving you an intro. But this is what geometry is normally taught like. Isn't this stupid and a waste of time?
Yes.
It is. Now, we're going to prove it and use this stuff later for stuff to actually do some cool math. But this would be all you do. And it's like, so here's my opinion on memorization and definitions. If you're not going to use it in your life, what's the point of memorizing it?
Exactly.
Right? Exactly. So, Here's why I think geometry is worth learning. Because it can challenge you. Memorizing and all that stuff isn't actually learning. It's not real geometry. It's a waste of time. Regular geometry class, how it's normally taught in school, is a waste of time. Because it's all memorization that you're never going to use. So what's the point? But in here, what we're trying to do is stretch your brain. Now, I don't care how we do it, whether it's geometry, algebra, whatever it is, right? That you're going to use the rest of your life. How to solve problems you've never seen before. How to think logically, right? But regular geometry class is just definitions for class. And I think it's a waste of time, which is why we do the proofs in here and all that stuff. Because that's less of a waste of your time. You might still think it's a waste of your time, but I think it challenges you, right? I could challenge you with English, I could challenge you with whatever and have your brain grow. I just do it with geometry. But definitions doesn't help your brain grow. But we need to establish some ground rules before we move on, okay? So this is just the intro. In regular geometry class, this would be like the entire meal, which I think is a poor meal. All right, so those are orthogonals. Number 3, what do you see? What do you see? What do you see? What kind of segments are those? Well, they're perpendiculars, right? But not just perpendicular. They're perpendicular bisectors because they bisect the sides, right? It cuts the side in half, and from the midpoint, it goes up at 90. Notice that where they go up to is kind of random, right? They won't always just go up to the vertex. In fact, doing that is kind of special, right? To have that hit at 90 is pretty rare. When they go off at 90, they're going to hit at random spots on the opposite side. Nothing special. We call these perpendicular bisectors because they're perpendicular and they bisect the sides. Not to be confused with angle bisectors, which bisect angles. Just fun to go back and feel what regular geometry class feels like. Boo.
You want to spell that first?
Perpendicular. Okay.
You want to spell that page?
Bisector. And the last one, by process of elimination, but still, look at the diagram. What do you see?
A lot of shared sides.
I see a lot of midpoints, right? Those aren't shared sides, they're congruent. Shared side means that they're shared, like how triangle AEC
That's what I learned.
shares triangle BEC, CE shared for both, right? So we see midpoints. Now, are they mid-segments? Remember, mid-segments are when we connect midpoint to midpoint. So no, we don't have the Triforce, right? We have what? Medians, vertex to midpoint. What have you noticed about all these?
Hey, stop watching me.
Center thing. I don't know. Dot. Middle.
They always intersect at one point.
Yeah.
Now, let's talk about lines. All right, so 2 lines, random lines. I'll draw them on the board. What's going on here? Because we're live. 2 random lines. Do they intersect?
No.
Well, I mean, they're lines. They go on forever. Will they intersect?
Yes.
Yes. 2 random lines. Will they intersect?
Almost.
Eventually, yes.
No.
How hard is it to draw 2 lines that will never intersect? Like, pretty freaking hard, right? Because they have to be what? Parallel. Drawing 2 parallel lines, pretty rare, but can happen. Right? So, for 2 lines, intersection happens often.
Where's that?
Parallel or no intersection, we should say, happens very rarely. Right? Does that make sense?
Yes.
That's for 2 lines. What do you think is going to happen with 3 lines? All right, I'm going to draw 3 lines randomly. All right. Now, do these 2 intersect?
No.
Yeah.
Yes, they will, right? Do these 2 intersect? Yes, they will. What about these 2? Yes, they will, right? So that makes sense. 2 at a time, the intersection's very likely, right? It's the same as this. Does that make sense? 2 at a time, yeah, they're going to intersect, right? It's pretty likely. But what about all 3 intersecting at the same time? Do these 2 and this all intersect at the same point? They won't, will they? I can extend it out. These 2 will intersect over here. This will go off, right? What about these 2? They intersect at one point, but will this intersect at the same point? No. We call intersecting at the same point concurrency. So, concurrency of 2 lines? Pretty likely, right? They're going to intersect unless they're parallel, right? But all three being concurrent, intersecting at the same point. Very rare, right? Very rare. So, what do you notice about these guys?
They are concurrent.
They're concurrent. The angle bisectors of a triangle intersect at one point. The orthogonals of a triangle intersect at one point. The perpendiculars are concurrent. They intersect at one point. And the medians are concurrent. They intersect at one point. That's pretty rare. Now, does that work for all triangles? Because all these triangles are the same, right? They're all acute, right? And I copied and pasted them. I just drew different lines on them. Does it work for all triangles? It's pretty rare for them to be concurrent, right? We're going to go to a magical land. Not this. This. Welcome to GeoGebra. I drew a triangle. Do you see it?
No.
What's its name?
What?
What's its name?
ABC.
It's not a very clever name.
You can name it Gregory.
Okay.
That's
Where is it? I can name the point. I can't name the triangle. Maybe he has a first name, second name, and third name.
yes.
What are we going to name this one? What's his middle name? I need a middle name. I need a middle name for this triangle.
Edward.
Joseph.
Jose.
Joseph? What? Last name, last name, last name, last name.
Joseph.
Nuts.
No, we should have done like
No.
Gatewood.
Lug nuts. What the?
We should have done like Haywood or.
It's not what I
Just
borrowed.
German.
Ray.
All right, so here's our triangle. Notice I can move them around. Right? I can make them a right triangle, make them a cute triangle, whatever I want. Obtuse, right? Very obtuse.
He's fat.
Hey, there are a lot less things, worse things to be than fat, like unkind.
He's also rude.
All right. So, enough.
I'm sorry.
All right. So, what do you want to make first? How about medians? Well, medians are what to what? What do we connect for the medians? Vertex to what? Midpoints. We need to find midpoints. I'm going to use the midpoint tool. Between Edward and Leibniz. That's the midpoint. Between Edward and Gregory. That's the midpoint. And between Leibniz and Gregory, that's the midpoint. Now I'm going to connect those up. Midpoint to midpoint or midpoint to vertex? Vertex. If I did midpoint to midpoint, I get the triforce. That is mid-segments, right? We're not interested in that. We're interested in medians. And check it out. All right, two lines intersect at a point. Shocking or not shocking? Two lines intersect. Not shocking, right? Dog bites man. But what about three lines intersecting at a point? Ooh. Man bites dog, right? Much more interesting story. Let's call that point D. For Derek. All right, now, this is an acute triangle similar to the one you have on your page. Let's try it for a right triangle. Oh man, it still all intersects at one point. What about obtuse? Oh yeah, still at one point. And not only is it at one point, but where is the point located? Inside, outside, or around the triangle? Inside.
Is this how you make the triangles?
No. I draw them in Microsoft Word. So, the medians intersect at a point that is always inside the triangle. So, let's write that, let's write that, let's write that, let's write that.
Technological.
For a right triangle, for an acute triangle, and an obtuse triangle. That's not a very good obtuse triangle. There we go. That's obtuse. So inside, inside, and inside. And this makes sense, because if you connect the medians, right?
What are you saying inside about?
Whoops. Then it intersects inside. The medians all intersect internally.
You don't have to write that.
What are you talking about?
You don't have to write that.
Sorry about that one.
Okay.
They all intersect inside.
Yes.
That's all I'm writing. I'll be more careful on the other ones. Now, what are we going to call G? Well, it depends on where you are. If you're in Eastern Europe, they call the intersections of medians the Medicenter,
We're not there though.
which is the one I learned. I don't know why. I've never been to Eastern Europe. But it makes sense to me. Medians, Medicenter, right? What we're going to call it, because we're America, is centroid. And it turns out, that's point G, that the centroid is the center of mass. Daniel, sit down and shut up. It's the center of mass. It's the balance point. Now, on a ruler, because it's equally distributed, the balance point's in the middle, right? Now imagine Xavier stands on this end, right? The balance point is going to have to shift way over here to balance him out, right?
Saying I'm bad.
I'm saying that you are heavier than the empty side of a teeter-totter, yes. So,
That weighed negative 15 pounds.
yikes. That'd be an interesting experiment. You sit on here and then, right, it goes this way. Anyway, balance point's in the middle. Now for a triangle, we got three different things going on here. So the balance point's a little bit harder to find, right? And as we pull one side further away, that changes with the balance point. So back to here. In an equilateral triangle, balance point's right in the middle. That makes sense. But as I pull this side away, watch where D goes. It goes with it, right? It's trying to balance that out. The further this extends in that direction, the heavier that side is, so the balance point travels with it. Now, we should not be shocked if we know that the medicenter or centroid is the balance point of the triangle. We should not be shocked that it's inside the triangle at all times. Right? Here's a ruler. Where's the balance point? Not over here, right? Of course the balance point's always going to be inside the triangle. That's what the centroid is, right? Doesn't matter what you do to it, it's going to be somewhere on the triangle. Even if you pull it really, really far, infinitely far in this direction, the balance point has to travel really far over here because it's going over there, right? It'll still be on the triangle. So that should not be shocking. Let's look at angle bisectors now. So angle bisectors, we're going to delete a lot of this stuff. Bye. All right. I'm going to create some angle bisectors. What's an angle bisector? It's a line that does what? Cuts the angle in half. So I'm going to go to angle bisector tool. And I'm going to go Gregory, Edward, Lovenuts. And now let's create a line that cuts that angle in half. Does it cut this side in half? Maybe. Depends on the triangle we're talking about, right? Sometimes it do, sometimes it don't. But it does cut that angle in half. We cool with that? That's an angle bisector. Now I'm going to do another one. Let's do Edward, Lovenuts, Gregory. Notice they intersect. Two lines intersecting. Shocking or no? No. Happens all the time. It'd be shocking if they didn't. What about three lines? Well, it's basically the triangle we were looking at earlier, so that shouldn't be too shocking. All right, I'll put a point there. Let's try a right triangle. Ooh. Inside, still intersect. What about an obtuse triangle? Still inside, but they do intersect at one point. Do you see it? This is not a coincidence. We're going to prove concurrency later. But yes, it will always be concurrent. This is the angle bisector center. Now, we do not call this the centroid, because the centroid is the intersection of the medians, right? This is the intersection of the angle bisectors, and we call it the incenter. So G is the in center. And we call it this because it has this property. I'm going to switch back. Check this out. Check this out. I'm going to pull this in. Okay? A is the center of something really special. I'm going to need a perpendicular first to do this. So I'm going to go from A to this side to make a perpendicular angle. Let me show you that that's different. See how that hits it at 90? All right, I'm going to put a point there. It turns out that A is the center of a circle that fits perfectly inside this triangle. Do you see it? Isn't that amazing? A is the center of a circle that fits perfectly inside the triangle. It touches each side at one point and one point only, right? It just barely kisses the other side is what they call it, right? They call it tangent. But we're not going to worry about that yet. So, if you want to know the biggest ball that you can fit in a triangular box, well, first you got to find the incenter, and then see how far the distance is from A to B, the radius. So take a look at our diagram. I'm going to draw a very bad picture in a second. Not like naughty, but like just not a good picture. All right. So check it out. That means that G to about, I don't know, maybe here, 90. Across to here is 90. Now notice sometimes it is right on the bisector, and other times it's not. I'm drawing from G to 90 degrees because I'm measuring to the side of the triangle. What do you know about circles? Radius, very good, right? From the center to the outside of the circle should always be the same. So from the center to the outside of the circle, which we know touches the sides of the triangle, right? Should all be the same because they're all radii. So there's a circle that exists here. Something like that. It's a poor circle. That's okay, we're not classist. So these sides are all the same. Now again, notice that the blue sides and the sides of the angle bisectors aren't always the same thing, right? Do you guys see that CE isn't the same thing as a blue side? Right? A lot of people think that little piece right there is going to be the radius. Not necessarily. See how F isn't the radius? Right? This is. Are we cool with that? My drawing is really bad, but do we see it? Just so happens that this one looks like it's going to be the same thing. Do you see how GD is the same thing as this blue segment? Right? But here and here it's not. Now when we measure stuff, we always measure 90 degrees. So when I measure from my head to the ceiling, I measure straight up 90, right? Perpendicular. I don't go, look, I'm really short because I measured this way, right? A lot of you guys, when you compare each other's heights, do that. Instead of going straight back, right? For 90, you go like, oh, look, I'm the same height as him, right? So when we measure stuff, we always measure 90. So from here to here is the same as here to here, as here to here. They all hit it at 90. So we have radii of an internal circle. Now, another word for internal is inscribed. We call it inscribed because scribe means to write and in means inside. We'll talk about this more tomorrow. Work on that self-development / warm-up. We'll devote maybe 10 minutes tomorrow to it. And I'll start the 10 minutes from the beginning of class. You lazies. Bye.
Is that?
It's so